Okay, so welcome everyone. Today we are very happy to have a local speaker, Vivek Shende, who is going to tell us how to glue the mirror.
Hi everyone. You'll have to forgive me. I'm not used to these Zoom talks still after a year. I'll do my best. So today I'll talk a bit about homological mirror symmetry. And I'm going to, in some sense, tell you everything I know about this subject. I'm not sure how well that will fit in this talk, but that's what I'm going to try and do. So from the beginning, what is it about? Well, you have some symplectic manifold. And you have some other a priori, perhaps unrelated algebraic variety. And from the algebraic variety, there's a category you can form. It's called the category of coherent sheaves. And roughly speaking, it's modules for functions on Y. And on the symplectic manifold, there's a category you can form, and it's called the Fukaya category. And well, being a category, it has objects. So objects are Lagrangians of some kind or another, Lagrangians. And it's important that they carry local systems, so equipped with local systems. But of course, you can always take just the constant local system. And then it has morphisms. And the morphisms are the intersection points. The morphisms between two Lagrangians are the intersection points. And it has some rules for composing morphisms. Composition. And this has to do with counting holomorphic triangles, counting holomorphic disks. And maybe it's worth saying that the left side of this picture is a lot more difficult than the right side. If you have an algebraic variety, it's given to you by equations. In principle, you can ask a computer, what is the coherent sheaves there? But if you have a symplectic manifold, it's some kind of, it solves some nonlinear equation, differential equation of some kind to even find what are the Lagrangians in there. You solve some further nonlinear equation to find holomorphic disks and so on. So it's a much more difficult, a priori, a much more difficult object to compute. And homological mirror symmetry is about the miracle that for some pairs of varieties, you get an equality between the Fukaya category. I guess people say isomorphism. You get an isomorphism between the Fukaya category of some symplectic manifold and the category of coherent sheaves on some algebraic variety. And this is great if you're interested in computing Fukaya categories, which you might be interested in for many reasons. They somehow invariance of symplectic manifolds. But it's also great for another reason. So as I explained, Fukaya category is hard to compute. But on the other hand, the Fukaya category, it's easy to construct somehow families of Fukaya categories. Symplectic manifolds, they deform with continuous parameters in a way that leaves the Fukaya category constant, whereas that isn't true for the category of coherent sheaves in an algebraic variety. In particular, often if you want to construct derived equivalences of a category of coherent sheaves, one way in principle you might do it is prove homological mirror symmetry and then deform the symplectic manifold. Okay, so that's what homological mirror symmetry is about. And maybe I want to give a few examples. Maybe the usual first example of homological mirror symmetry, first somehow conceptually, not historically, is you look at the cotangent bundle of the circle. That's the symplectic manifold. And the corresponding algebraic variety is the punctured plane. And the way this correspondence works is that, so I'm going to now tell you somehow what objects correspond to what. One Lagrangian in this symplectic manifold is the zero section. And on the zero section, I said before you can put a local system, and a local system on a circle to focus on one-dimensional vector space, and the endomorphism of the one is an invertible complex number.
Vivek, at least for me, you're breaking up.
Complex number.
I don't know for others, but for me, you're breaking up. For me, you're breaking up. Maybe stop the video. It might.
I see.
It was fine for a while, but then it wasn't. So.
Okay, so I've stopped the video. Just please let me know if that happens again. And
actually, Vivek, I'm sorry. I have a question before you go on.
Okay.
Is this supposed to? I think you may have said this, but I just missed it. It certainly works. It should work well for derived categories. How about before deriving? Does it? How well is it?
Yeah, of course. No, it doesn't work at all. And I have been derived for too long. So when I said coherent sheaves, I meant the derived category of coherent sheaves.
But then I don't understand something because.
Maybe
then, okay, I guess you're simplifying things a little bit, right? Then the things you said on the left are not quite correct, but we've simplified things a bit.
Coherent sheaves, let's say derived category of, and maybe you're complaining that here I should have taken,
I'm not complaining about anything. I'm just trying to understand the statement. And if you tell me that I should understand everything the way in the derived sense, then I think I'm okay.
And here I take triangulated envelope.
What do you mean before deriving it doesn't work at all? I mean, there are many of cases where you can find T structures on both sides.
Yeah, okay, but you can repair the fact that it doesn't work.
Well, what I just meant is what physicists would think about distinct brains, or the same brain rather, are really objects of the derived category and not before deriving, for example, not in the A model. So even before we worry about stability conditions, from what I understand of derived categories, they actually behave much better in terms of our physical intuition of what brains should and should not be doing, rather than the simpler things which keep somehow too much information about, for example, on the coherent sheaf side, exactly what the complexes are and so forth, like themselves as opposed to isomorphisms and things like that. So. I mean, yeah. Then, for example, what the morphisms? Well, I don't know. I mean, in principle, one could just talk about the bare A model, and maybe there's something there that makes sense in the mirror symmetry. For example, if you talk about morphisms just being intersection points, as opposed to taking cohomology and things like that.
Okay, maybe we can discuss that at some other time. It won't play a significant role here. I will stay in the derived setting throughout. Maybe throughout until the end. Maybe at the end I'll have to discuss T-structures, but for a long time I will not. Are there any more questions about the this kind of basic outline of what is mirror symmetry about? Okay. Let me do a few examples. So if I take the zero section and I put I was saying I was going to take a rank 1 local system on it. Such a local system is characterized by its monodromy, and its monodromy is an element in C star. And what mirror symmetry does, maybe I'll explain why, give a construction of this later, is that it would send this object to the structure sheaf at that point. And there's another Lagrangian that is natural to consider here, which is the cotangent fiber. And what mirror symmetry does is it sends the cotangent fiber to the structure sheaf. I haven't explained to you why that is. There's many different reasons why it's true, and I will come to some of them later on. I just want to get a sense of how this dictionary works in everyone's heads. But I said before that this is supposed to be an equivalence of categories, and so it should take morphisms to morphisms. And so if I
Vivek, just maybe for the purpose of students in the audience, just draw a few pictures, because many may not know actually what a tangent fiber is and so forth.
I will draw them right now. So here is the cotangent bundle of S1, and here is the zero section. And here is a cotangent fiber. And I told you before that Hom and the Fukaya category should be intersection. And indeed, there's one intersection between the zero section and the cotangent fiber. And on the other hand, Hom from O to the skyscraper point is indeed one-dimensional. So that sounds pretty good. But you might be concerned that Hom from O to O, well, this is the Laurent polynomials in one variable. And I'm somehow supposed to extract that from the self-intersection or whatever of this cotangent fiber. So let me explain how that comes about. Well, first of all, whenever you calculate self-Hom, you're supposed to perturb a little bit. Okay, so I'll perturb a little bit. It's not so important how you perturb a little bit, but I'll do it this way. And then, okay, so now it looks like there's one intersection, which is not great because this is a countable dimensional vector space, this Hom. And the basis of that countable dimensional vector space has to do with at infinity. And the way you think about those is you ask for what are called Rabe trajectories that go around. So this is a Rabe trajectory. In this cotangent bundle case, Rabe trajectory is just the same thing as geodesic flow. So the Rabe trajectory is, well, you can go once around, you could go 2 times around, and you could go, as many times around as you want. And also on the bottom, you could go once around, or you could go 2 times around, or so on. And so on one side, maybe the way this correspondence works is that on maybe the top, you get the positive powers of t. And on the bottom, maybe you get the negative powers. And I haven't, and I won't at the moment say anything about the composition maps. You somehow have to count certain holomorphic triangles. And even in this example, that's not completely trivial. But I just wanted to get this kind of basic picture of how this correspondence is supposed to go. Are there any questions about this example?
And you think of getting these read trajectories by this kind of perturbation that you turn on some kind of Hamiltonian near infinity and wind the Lagrangians themselves.
I mean, there's various ways you can think about it. You can just declare that you count Rave trajectories as intersections. Or you can say that you turn on the somehow, standard quadratic Hamiltonian for the cotangent bundle and you take actual intersections.
And they're all equivalent.
They're all equivalent. So maybe just to say the words, including the intersections at infinity is what people call the wrapped Fukaya category. But I will just call it the Fukaya category. That was the example of the cotangent bundle of S1 and C star. And so the next picture I would like to draw, you can partially compactify C star to C. And I would like to explain what corresponds to that. So what I will draw is this picture. Okay, so it's a cylinder with on one end, 1 point distinguished. And this point is what is called a stop. And the way that the stop, okay, so let me just now say the dictionary again. So as before, if you take this zero section and with this kind of local system, exactly as before, it goes to the structure sheaf at that point. If you take the cotangent fiber, so maybe I'll draw these like I did before. So the zero section is this yellow one. The cotangent fiber is this green one. And then there is, there's one more. So the cotangent fiber, it goes to O. And there's one more, which I call a linking disk. And it's somehow associated with the stop, and it looks like that. Okay, and that linking disk, well, when I was making the structure sheaves of points, I left one out, namely this point 0. And that goes to this point, the point 0. So let me comment just briefly about how this stop modifies the rules for intersections. So all the stop does, it modifies the rules for intersections at infinity. And the way it does that is that now you only count these Rave trajectories which do not meet the stop. So before I was taking trajectories at the top and the bottom. So I'll still have the ones at the top because they don't meet the stop, but I won't have the ones at the bottom anymore. And so, in other words, I keep only the positive power, what corresponded before to the positive powers of T. And well, that's pretty good because indeed Hom O now is only positive powers of T. because I have functions on the complex line. So you see that this business of having the stop, which is some kind of rule about how you do intersections at infinity, tells you is the right thing to produce this category.
Okay, so I have a question.
And as I said before, okay.
Yeah. So could you tell us a little bit about how this was discovered and also about by whom? In other words, did people discover this by studying
to be honest,
superpotential? Or did you discover this?
No, I certainly didn't discover this. I'm not 100% certain about the history. So I'll talk about superpotentials in a second. Probably it came from thinking about the superpotential, but it was, so to speak, whenever this was discovered, it was before my time studying the subject. So you'd probably have to ask Denis or Paul or one of those guys. But I mean, as you asked about superpotential, let me at least talk about.
It would follow from the superpotential that Hoare-Waffe wrote down by the prescriptions that they essentially wrote down in the paper.
Let me just explain. Let me just explain the relationship with the superpotential for people who don't know what it is. So what Mina is mentioning is this this Hoare-Waffe superpotential. And what this is, it's a map from, in this case, it's a map. This whole discussion right now I'm having on the side I compute Fukaya categories on. So it's a map from C star in general to the n to C, and you can produce from such a map the way you produce a stop from this map is this map from C star to C. It's like something. Okay, this is here is C. Maybe it's not so important. This is C star to the n. So let me just call it X. So X is someone up here, X. And X is some symplectic manifold. And the way you get from this kind of Hoare-Waffe superpotential to something with a stop is you just take a point at infinity in C, and you take the preimage of that point. And this, roughly speaking, is your stop. Okay, and so the prescription for in this example, this kind of partially wrapped Fukaya category having to do with this stop comes from a Hoare-Waffe superpotential in the following way. You take in this example, you take just the inclusion of C star into C. That's the superpotential, just the function Z. And then, the preimage of a point at infinity gives you one point at the boundary of C star, which is the picture which is drawn here. That's this business about superpotentials. And if you come from the Seidel school of computing Fukaya categories, then you study somehow Lefschetz vibration. Then you maybe somehow the Seidel school. You then hope. So I think they usually call this map W. You hope W is a Lefschetz vibration, or maybe you deform it to being a Lefschetz vibration. And then you use vanishing cycle methods. So I somehow don't do this and not competent to do it. And for today, I won't discuss it any further. that's kind of maybe the way, the way people studied this subject before I learned any symplectic geometry.
I think this part is useful only if you want to have, some nice sort of set of brains to work with. But otherwise, you don't really need to think. You can think about it the way you're thinking about it and be just fine. But there's some set of brains that generate the entire category, and the ones that cite these symbols are a good set of bases. For the same reason, working with line bundles in C is a good thing to do. But that's about all. You certainly don't have to.
Well, yeah, but there's also there's somehow thimbles. From my point of view, thimbles are by accident what the cocores happen to be for a certain Morse function that is associated to a Lefschetz vibration. There's in the setting that I work in, there's somehow a natural generalization of thimbles that always happens. But anyway, let me not discuss further this Seidel school point of view. I want to continue.
Sure. What's the family of A-branes that interpolates between these local systems over the zero sections and this linking disk?
Maybe you're asking the question of here I said that the branes on the zero section, they are the structure sheaves away from the point at zero, and the linking disk is the structure sheaf at zero. And I guess you're asking, okay, why is it that
the yellow guy special blue guy, exactly.
Yeah, this one specialized the other. So the way you make that is, maybe it's easier in sheaf theory, but let me just tell you in terms of these Lagrangians. So the point is that you can make you can create everyone as a cone on a morphism from the cotangent fiber to itself. And that morphism it comes in a one parameter family, and for values of that parameter, gotcha, which are not zero, then you get one thing, and it's something like that.
Yeah. Okay. Thanks.
Actually,
yeah. I mean, it's like
I think what I said.
Generate. So sure, you can write it in terms of that. Fair enough. Okay.
I think what I said is slightly incorrect. You make a certain. Yeah. Sorry. Let me try again. You make a certain complex out of the linking disk and the cotangent fiber, and maybe like two cotangent. Okay, let me not try and do it on the spot, but it's of that nature. And the nature of the specialization is that a certain map becomes zero.
Sounds good.
Okay. As you'll see,
Vivek, actually, there's something
maybe
interesting.
The lesson of my talk,
which is that once we turn on equivariance, which we'll do in a moment, the simple circle Lagrangian actually doesn't make sense anymore. Which is obvious from the mirror perspective, because only the zero brane that sits at the origin of C is invariant under rotations. So I didn't quite understand.
Well, let's discuss that. Let's discuss that once. Let's discuss that once we get to equivariance. I want to say something about all these questions about particular objects. The lesson of this talk is supposed to be that in proving equivalences of categories, actually you should never think about objects. So I don't want to get too involved in the individual objects, because once we get down to actual work, I'm not going to discuss them. But let me do one more. Mostly I give them so you have some idea in your head. So let me do one more example, which is P1. Okay, so I think maybe maybe I won't bother coloring it this time. So this cylinder is supposed to be mirrored to P1, and now I put two stops, one at the top and one at the bottom. And it's like before, where a local system on the zero section, it goes to, again, the structure sheaf at that point. Now there are two linking disks, this one and this one. And maybe I'll call them d0 and d infinity because I guess maybe I'll just keep this one. At d0, it goes to the structure sheaf at 0, and d infinity, it goes to the structure sheaf at infinity. And still the cotangent fiber goes to the structure sheaf. So that was just some kind of examples to, give you a picture to carry around in your head. And I haven't pretended to do any proofs of anything so far, maybe just given some kind of plausibility arguments. So now I want to discuss a little bit how you prove things. And of course, in this kind of small example, there's many ways to prove things. One way is by hand, you find enough objects to generate the category, you prove they generate the category, you compute Homs on both sides, you match them up, you make some further arguments about and not having to compute higher Homs and so on. And anyway, it's like kind of a lot of effort even for doing these examples by hand. But what I'd like to explain to you is how not to do that. And so I have to now dip into a bit of general theory. So this is a general theory. And the general theory, this is the general theory for computing Fukaya categories. And the general theory I'll discuss here is only applicable to the exact case. So for, let's say, Weinstein symplectic manifolds. And I mean, as I mentioned before, there was kind of the old general theory, which was this kind of this Paul Seidel-Lefschetz business. And this is not that. This is the general theory that you will find in my papers with John and Shield. This is now a GPS series. And what I'll explain right now is mostly in the second of those papers.
What does Weinstein mean?
Weinstein means, yeah, so maybe I should say that. So what is, what is this thing? So this kind of symplectic manifold, in general, a symplectic manifold is a manifold and a symplectic form. And it's called an exact symplectic manifold if the symplectic form is D of something. And it's called Weinstein. So, okay, so in general, for an exact symplectic manifold, being exact is the same thing as there being a vector field Z where which scales the symplectic form, because the relationship is that then omega Z, whatever is lambda. And being Weinstein means that, okay, so first of all, there's a word called, this is called the Lyrical vector field. And it has some kind of flow. And being what's called the Lyrical manifold means that somehow you're non-compact, but somehow your non-compactness is kind of exhausted by this Lyrical flow. And being Weinstein means that, so you can ask, okay, let me now take everything that was not sent off to infinity by the Lyrical flow. That's what's called the core or the skeleton. This is the what does not escape. And being Weinstein means that, I guess no one can actually see this red color. So Weinstein means that oh no. This is some kind of disaster here. This one? No. This one. Okay, so Weinstein means that the core is isotropic. It's difficult but not impossible to produce examples of Lyrical manifolds which the core is not isotropic. So this was the answer to the question: what is a Weinstein manifold? Okay, and so for example, cotangent bundles are the most basic example, but that's what it is. So let me get back to this discussion of this general theory. Everyone, give me 1 minute. I'm gonna go consult my tech support and try and fix the problem that I'm having here.
All right, Mina, while that's happening, could I ask you if this whole business about stop follows from the Hori-Vafa thing? Because Hori-Vafa use these exponential coordinates. So when Vivek says stop, oh no, Vivek's back. I don't know what's happening. Anyway, I was just going to ask, when Vivek says stop, is that just because in the exponential coordinates of Hori-Vafa, there literally just isn't room, it's not in the domain to study array vector flows or whatever kind of quadratic Hamiltonian perturbation?
So what you do, right, is if you study symbols, then they are non-compact. So to compute the intersections, you so there's some kind of Lagrangians where, say, imaginary part of the superpotential is constant, and then they deform to be able to define intersections. It's you know, because otherwise they're just like on top of each other, like it's just even a self intersection. You compute symbols of imaginary W constant and imaginary W times the phase being constant.
Mm-hmm.
And that will or will not have an effect depending on how the superpotential behaves. So for example, in the C exam, yeah. So the places where he gets a stop, this kind of winding that he was drawing for at infinity doesn't happen. So it's encoded in the superpotential. The superpotential simply tells you that
Okay.
you don't wind.
I see, gotcha. Oh, okay, cool, even better. Thank you.
Okay. So I'm back. So I want to explain a few of these general principles. So the first one is that maybe I'll call it 0. Maybe I'll call it 1. The first one is that stop removal is the same. I mean, doing a stop removal in geometry. Maybe okay, sorry about this. I'll explain these principles in the following way. There's geometry, And then there's effects on this category, categories. And the first thing is that stop removal. It goes to quotients of categories. And some kind of example is that if I take this, you remember that this was this thing was co A1. Oh, maybe I've done the wrong kind of drawing. So if I remove the stop, just take away the blue thing. Well, you remember that this thing was supposed to be co A1, and this thing had the Fukai category of this thing was supposed to be co of C star. And this stop removal is supposed to be the quotient. And remember that it's the quotient by the category generated by the linking disk. And so what the general theory tells you is that what this goes to is it goes to doing the stop removal, transforms this to co A1 mod whatever is generated by the linking disk. And remember that the linking disk, it was the structure sheaf at the origin. And indeed, the quotient of co A1 by the subcategory generated by the structure sheaf at the origin is modules over whatever's left, namely C star. So you see from this kind of general principle that knowing the mirror symmetry with the stop implies the mirror symmetry without the stop. So that's principle one. The next thing is that products of spaces, this one should not be so surprising, products of spaces. This goes to somehow tensor product of categories. So there's some kind of Kunis formula.
Can you say a little more precisely what you mean by the quotient, just so we?
Well, just when you have a category and a subcategory, you can take the quotient. It's I guess it's the universal thing.
Okay. So should I think of it like
the quotient is yeah.
Any.
So sorry, I didn't hear your question, Nina.
So you simply send everything that comes from the subcategory to 0.
That's right. Is that a good enough answer?
Yes.
Okay. Then the third principle is that somehow what's called sectorial, never mind what this is, I'll explain later. Sectorial gluing, I mean, never mind the word sectorial, but certain kinds of gluing, which is roughly speaking, gluing along stops. Arnav is saying some kind of category theory words, which I don't know what they mean. Arnav, I take in effect, I'm quotienting by the triangulated subcategory closed under summands generated by those objects.
Okay, sounds good. Yeah, sorry, when I posted in chat, I wasn't aware you were looking at chat. I thought I was just asking the other people who were in here. Sorry, go ahead.
Oh, I see. Okay, so sectorial gluing, or in other words, gluing along stops, that becomes a push out. And okay, so that's principle 3. And then maybe the fourth principle is that a collection of disks transverse to each connected component of the smooth locus, maybe smooth Lagrangian locus of the skeleton, these go to generators.
Actually, I do have a question about this. Still going back to these quotients. So we started with some nice category of Lagrangians. It's not obvious where sort of every object is an actual Lagrangian as opposed to something formal that doesn't come from a Lagrangian, but you could. It's a little bit easier to imagine these things. Sometimes adding complication actually makes things simpler. So working equivariantly makes things simpler, makes it more obvious that some things are sort of don't come from Lagrangians. But was it obvious that that this? So in particular, it's not obvious to me that taking quotients, you would land in a category that's still nicely generated by Lagrangians, as opposed to not.
I mean, this item 1 is a theorem. It's not obvious.
Okay. It's not obvious that it works. Okay. I see.
No. It's that's maybe this theorem. This first thing is maybe the main engine of this GPS2 approach. I mean, none of these four. I mean, certainly principle 3 is not obvious. Principle 4 is not obvious. 2 may be obvious, but the rest are kind of. I mean, I would say proving items 1 through 4 takes about 100 pages. But we know them now, and so.
I'm sorry, I just missed the number 4. Could you just repeat what number 4 says?
Number 4 says that if I take a collection of Lagrangian disks, satisfying appropriate conditions at infinity, I mean the usual ones, such that you have one disk which meets each connected component of the smooth Lagrangian locus of the skeleton, then those disks generate your category.
Okay, so it's some prescription, which I didn't follow in real time for figuring out what the generators are.
That's right. Maybe I'll just like the zero. I'll do one example of that. But just to say that people usually call these somehow cocores. And then just the example of number 4, if I have if I have this surface, then you can work out that its skeleton, when you put an appropriate choice of symplectic form, maybe its skeleton looks like this. And here is one disk transverse to each connected component of the smooth Lagrangian locus of the skeleton. And so an instance of this theorem 4 says that these 3 blue guys generate. Okay. Yeah, by the way, I assume that as usual, I have like 2 hours or something. So I somehow just going to continue for some time.
Yes, exactly.
That's right, Mina. Okay. So I continue for some time. So Let me go back to doing some examples to illustrate how to think in terms of these rules. So now I'm essentially going to give maybe closer to giving proofs of statements. Okay, so let's consider the cotangent bundle of R. Well, the cotangent bundle of R, here's R, here's its cotangent bundle. Just for the heck of it, I'll draw the Lyrical flow. Looks like this. And in the cotangent bundle of R, there's more or less one Lagrangian you can ever imagine, this one. And you can compute that somehow, I'll call this F, and you compute that Hom F, well, I said that you're supposed to perturb it a little bit, and then you look for Rabe trajectories, there aren't any, and so Hom FF is just C. Okay, so that's a more or less honest calculation. And this principle 4, or just thinking about it for a few minutes, will tell you that F generates the category. So in fact, the Fukaya category of T star R is modules over Z. I'm not going to make so much, I mean, strictly speaking, for the category theorists, I should have said something like the co-completion of this category is mod Z. I'm not going to, I always take ind of all my categories. I'm not going to dwell on that point. There's another name for this T star R, which is that I could also have called it the disk with 2 stops. You can kind of, and then that one Lagrangian from before looks like this. So let me do a little bit more complicated example. I'll do the disk with 3 stops. So either some business with skeletons or just thinking about it will convince you that these Lagrangians generate.
Okay, let's try again. What does the stop mean in this context?
It is a rule for telling you how to compute intersections at infinity.
Okay, and so just explain the rule in the first example with a disk and 2 punctures and at the boundary.
Yeah, this one.
So just say
so the rule is, so I mean, I had better try and compute something. So let's try and compute Hom from this this Lagrangian to itself. So here's another copy of it. I've perturbed it a bit. And I should include some trajectories at infinity. And specifically, I include the trajectories, I include trajectories that do not meet the stop. So because these trajectories run into the stop, you know, this, but it meets the stop, so I don't count it. So there are no intersections at infinity here. So this would tell you that this Hom space, so we're calling this F, Hom FF, it's really just that intersection point. So, I mean, Mina, for you, the way you would think about, I guess the way you would think about this space is you would think about it as being the space C with the superpotential Z squared. Because that would pick up for you 2 like points in the pre-image of a point infinity. Is that okay?
Perfect. Excellent.
And so now I'm going to take 3 of them. And let's take these Lagrangians. And well, now, I mean, I've drawn them in such a way that there's one trajectory at infinity. It looks like this. And I don't include this trajectory because it meets the stop. Okay, so we don't use this one. And either by some yoga about Skeleton, or just kind of looking and thinking about it, you can convince yourself that these 2 Lagrangians generate. And again, if you were to look at one of them in isolation, you would see that its self-harms is just the integer, is just somehow generated of one thing. So in other words, the Fukaya category of the disk with 3 marked points, this is modules over this quiver. Because these are the 2 Lagrangians and there's one morphism between them. Incidentally, another way to kind of see this is if you look at this category, whatever it is, if you take the quotient by this green one, you have to, it's the same as removing the stop, and then we get back to the just modules over Z itself. So, okay, so these were some kind of calculations more or less you do by hand, but let me explain how you use this kind of gluing to put them together. So here's an example where I actually illustrate this kind of general methods. So this is the example of the P1. That's the mirror to P1. P1's mirror. Okay, so remember I told you that was supposedly going to be a cylinder. So I'll draw a cylinder where I put a stop at the top. So these are the same. I put a stop at the bottom. So this is supposed to be P1's mirror. And let me prove that to you. So the proof is the following. It's that I introduce 2 kind of fictitious stops. I introduce this one, and I introduce this one.
Actually, Vivek, sorry, I'm sorry, I missed something. Actually, yeah. So we started with T star R, and then you said that this is the same as C with superpotential Z squared. I understand it from the answer, but was I supposed to have seen that this would have happened anyhow?
Yeah, that T star R is the same as this thing with 2 points. Yeah, that the point is that how to say, let's look at the Lyrical flow on this disk. So usually the Lyrical flow on the disk looks like this. It's just radial. But the radial Lyrical flow, it doesn't really respect the fact that there's a stop here. So in fact, there's some kind of natural prescription for what you do to the Lyrical flow when you reach the stop. And what it is, it looks something like this. And so now looking at that picture, you can kind of see that it looks like this Lyrical flow on T star R. And if you want the somehow formal version of what I just said, you would have to read GPS 1, chapter 2. Section.
So this says that these Lyrical flows interact with a superpotential. They know about a superpotential, right?
Yeah, basically, well, it's similar information with superpotential, yeah.
I mean, in the A model, right? The superpotential comes into, well, it comes into everything. In other words, it comes, for example, into the instanton equation. It comes into the equation for the intersection points as some kind of preferred Hamiltonian deformation. One could think of it like that: that there's a, some preferred Hamiltonian symplectomorphism that you turn on, even if you it simply, or you can undo it by that effect. Should everything have been compact? Did you? Is the Liouville flow also kind of is the same kind of deformation? So maybe the two are just simply the same.
The Liouville flow is not. What is the same? I mean, the way that this Hamiltonian deformation you're discussing kind of interacts with the stop at infinity is that basically the Hamiltonian deformation that you want to use is somehow like 0 at the stop, and it's kind of non-zero everywhere else. The relationship with this somehow corrected Liouville flow is that again, this Liouville flow has to like turn outwards at the stop, like in this picture. But I would say it's all kind of all similar information. It's some way of prescribing. I mean, from my point of view, in terms of just studying the category, it is not important that you have one particular preferred Hamiltonian deformation. There's a certain natural, quite large class of Hamiltonian deformations, basically characterized by being 0 on the stop and positive elsewhere, that all produce the same category. And somehow, any particular, like the particular choice of superpotential is one such item.
Yeah, this makes sense. That's
okay. So let me just do this example of P1's mirror. What you're supposed to see from this picture is that, well, I've taken 2 copies of this disk with 3 stops and glued them together along 2 of the stops. And if you look a bit more carefully, that gluing identifies those 2 Lagrangians that are next to each other. And so, well, if you believe my somehow calculation from before, this gluing principle tells you that the Fukaya category of this item, whatever it is, this whole thing with those yellow things just kind of fictitious, is equal to some kind of push out of the Fukaya category of this 3-punctured thing, another copy of it, and then somehow this gluing region. The gluing region, if you think about it, it's actually a copy of the Fukaya category of the disk with 2 punctures, and there's like 2 of them.
Can you explain this just a little bit more slowly?
Like kind of co-limit. Yeah, sure. I've taken 2 copies of the 3 marked point disk. Let me just shade one of them in. So this is a copy of a disk with 3 boundary marked points, namely the white region and the 2 yellow regions. And its complement is also a disk with 3 boundary marked points, namely the white region and the 2 yellow regions. And that's the Fukaya category of this, disk with 3. I mean, this item is this item here. And maybe I can shade the complementary region in blue, blue, and blue. And I haven't told you exactly how to assign something meaningful to their kind of overlaps, but what you assign to their overlaps for somehow maybe kind of long digression, I'd have to explain it, is the Fukaya category of either a point or somehow this thing with 2 marked points. But I mean, just to say, let me finish this calculation, which is that this is modules of this quiver. This is modules of the same quiver. And here we have modules of somehow the quiver with 1 point, and I include it somehow here. And here I have modules over the same thing, and I include it here. And if I were to take this colimit, well, you can convince yourself that this is equal to modules over, I just glue this one to itself. And so that's some kind of, you can, if you want, turn that into an argument that indeed this Fukaya category is the same as the coherent sheaves on P1, because it's well known that this thing is called P1. And if you wanted, you could then invoke stop removal to deduce the things I was claiming for A1 and for GM.
How do you show that such? How do you show that such a thing is true? Just like I mean,
which thing is true?
Well, that these categories behave so nicely under operations. Like, what's the operations of gluing? That this actually works.
You mean this theorem 4? That's
right.
Like I said, that's about 100 pages of mathematics. It's kind of a long story. I can maybe I'll give you some kind of cartoon about why that's true.
Sorry. So you're telling me that this is direct. The fact that it glues so nicely is a direct consequence of your property 4. Is that?
I mean, that's the statement. That's what property 4 is saying. It's saying that.
I see.
That's what property 4 asserts. That this kind of cover, it goes to a colimit. The cartoon, maybe I'll just give you the cartoon picture of why this is true. And the cartoon picture of why this is true is you have this kind of, some kind of space X, and your viewing X is glued together out of some, maybe I wrote X in a bad place. The whole space is X. And your viewing X is glued together out of, let's say X1 and X2. And the way you prove this kind of thing is you, if you were to study X2 by itself, well, it kind of has, it would look like it has a stop along this region here. And so what you do is you introduce some extra stop for X2, and you introduce some extra stop for X1. And now what happens is that the category which kind of lives in here is like the category which X1 had originally. And the category which lives in here is like what X2 had originally. And the category which lives in here is kind of the category of their overlap. And now that's some kind of, and there are some morphisms, namely there are morphisms in this direction and in this direction. And so the category of X with these two new stops introduced, somehow geometrically you can see that it's what's called the growth and deconstruction built from the green part and these two red parts. And then you have to remove, you want to then now delete this, delete, and delete. And okay, you delete those things, and it's some kind of fact of category theory that if you form this growth and deconstruction and then you localize it in a certain way, then you get the push out. And the basic reason why this gluing holds is you can introduce stops to make your category compute the growth and deconstruction of these subcategories in this way. So this is the cartoon of the proof of that thing. It turns out to be very useful to be able to introduce stops to somehow modify your categories in certain ways.
Vivek, can I ask one question?
Yeah.
It's Peng. Yeah. So you mentioned this is a mirror to this core of P1 by using that quiver description of P1. In general, I was wondering, how can the decomposition of a skeleton be matched on the B side?
Yeah, I have no idea. That's a good question.
Okay.
I mean, you see from this picture that the answer is not going to be natural in terms of the like classical algebraic geometry of the B side.
Right.
Because there's like some derived equivalence or something. Okay. Good. So now I want to get to some relatively newer things. That was still all the kind of warm up of this. Maybe I'll take some. The warm up of this talk is now finished. I'll take questions about anything that's happened so far. Okay. So let me discuss some new things. And so as Mina has wanted to hear sometimes already, I want to say a few words about equivariance. So there's some kind of remark, which is if you take G, which is Hom from pi 1x to the multiplicative group, this acts on the Fukaya category of X. And the reason this is true is that I told you that the Fukaya category, the objects of it are Lagrangian equipped with a local system. And well, an element of this Hom is a local system, and you can just tensor by it. You can just tensor it. So you tensor by tensor in the local system. Okay, so that's a kind of G action. And if you want to take the invariance, like the equivariant, the G equivariant category, I claim that this is true, that this is the same as taking the Fukaya category of the somehow abelian cover of X. Yeah, since I have, do I still have, is Arnav still in the audience? Yeah, since I have some like category theorists in the audience, maybe I can ask, I realized I was confused about this, so somehow question, what exactly were, in what sense is this true? So in precisely what sense is this true? I'm sort of confused about, I mean, I think maybe it's like literally true if I work over C, but I'm a little bit confused about in what sense this is true and over other rings and so on. But just to explain, you know, like roughly speaking, why is it true? Well, taking the G kind of invariance, well, that means that you want to trivialize the G action. And if you want to trivialize the action of tensor product with elements of pi 1, well, you can do that by going up to the cover, which if you want to trivialize the action of tensor product with a local system, which is an abelian representation of pi 1, well, you can go to the place where there are no such abelian representations, namely the universal abelian cover. So this thing as stated is not necessarily something I believe. Let me state the version of this. There's a version of this which I believe, you know, because let me tell you the reason I don't believe this version as stated is that, well, maybe the Fukaya category of X is like 0 or something. It doesn't know anything about the geometry of X at all. So I'm not sure if you should believe this statement, but the statement which I believe and about which I would like to ask this question is suppose, so given a sheaf of categories on lambda, same question, same question for the global sections of this sheaf versus G equals Hom pi 1 lambda G. And I guess the sheaf of categories is somehow like, which emit somehow tensored over mod K. Okay, so I realized that I somehow, my category theoretic abilities are not quite good enough to say exactly what's supposed to be true here. But it should be something of this nature. And let me explain.
So you're just Vivek. The left-hand side is some equivariant Fukaya category.
Yeah.
Equivariant with respect to G. And are you going to tell us what you mean by this? Did you tell us what you mean by this?
You know, I'm slightly confused in that if G were a finite group, I would know what I meant. It would mean that, you know, I take like an object together with an isomorph, like some system of isomorphisms to like what happens when G acts on that object. But when G is an algebraic group, I'm slightly confused about what exactly I'm supposed to say. In particular, whether I'm supposed to say somehow compatible things for the K points for all K. Anyway, I'm slightly confused about it. But roughly speaking, what it means is that, you know, like what you would do whenever you have a group action on the category. The equivariant category is like an object of the category together with a system of isomorphisms to whatever you get when G acts on it.
I wouldn't have guessed, I mean, I don't know. I wouldn't have guessed that the algebraic group nature of GM or GM to whatever power is the real deal breaker here. I would have guessed that it was something about, do you want to enforce something about local constancy versus constancy, that kind of deal. Maybe I'm like thinking completely the wrong direction.
What do you mean local constancy versus constancy? Well, let me tell you the reason I was concerned. Like, you know, like if I was working over the field of two elements, then maybe there's just not so many maps from pi 1 to GM. I mean, that's why I'm kind of concerned, as opposed to like.
Gotcha. Okay, gotcha. I see.
But I think the statement is kind of literally true over the complex numbers. Maybe even just viewing that as a discrete group. But I'm going to I'm just going to carry on. Yeah. Yeah.
Hi. It might be nicer if you. So this is a little weird because, right, you are looking at the algebraic group acting on the mirror, and then taking the quotient of the Fukaya category by that. I mean, I'm just thinking of like the application you have in mind. And it might be easier if instead you looked at the action of the deck transformations on the abelian cover.
Yeah.
And then that can be matched with quasi-coherent sheaves on BG.
And let's see. You're saying you're saying that I start on the other side.
Yeah.
I begin with Fukaya category of X tilde abelian. I study the action of the deck group on that, and then somehow that's supposed to tell me about the other side.
Yeah, and then you can basically use like the DX. I mean, it's the exact same thing you're doing. I'm just saying it's slightly nicer in that the deck transformations are like visibly acting like in a symplectic way.
Okay. maybe we can discuss that. We can discuss that afterwards.
Okay. Yeah. I mean, it's no different, like mathematically. It's just.
Yeah. Anyway, I'll be quite happy if someone can explain to me what is the correct way of making this statement. Because as you'll see, it's a quite useful statement. It's definitely true in some sense, but somehow I'm a little bit confused what words to say to make it true.
I'm still confused about what you're doing. Are you dividing by G, or you're working equivariantly with respect to G? They're not the same, not in my world.
Let me give you the example. Let me say what I mean on the mirror.
Can we do the example of C? That's a good one to do.
Yes. So for example, let's go to the mirror so I can study co-C. This is, well, everyone knows this. This is like mod, KT inverse, KT. Now you can study C mod C star. And if you ask someone who is somehow homotopically enlightened in a sufficient way what this is, they might tell you something like that this is co-C somehow C star. In other words, that C star, after all, it acts on co-C by pullback, and that just from that action and somehow some formal categorical construction of making invariants, you recover coherent sheaves on the stack. In fact, that's supposed to be basically a definition of coherent sheaves on the stack.
Okay. So in a physicist world, the way you want to think about doing what you're doing, I think, is in two steps. First, working just equivariantly, which means I have a group action. I just keep track of grading of everything inside under the group action. And then in my next step, I could decide to quotient, which means to just keep invariants. This is how we think about gauge invariant, like gauging anything. So I would have liked you to explain the first step, which is what I would call an equivariant category of A-brains or something. And then in the second step, explain how to take quotient.
This one should be your equivariant category. I mean,
again, because of my confusion.
C star acts on co-C by pullback. Now there is something which I have realized my category theory is not good enough to say what it is, where using the data of this action, I can form coherent sheaves on the stack quotient. And yeah, that's so I'm not sure what distinction you're making between these two items, Mina.
In the first case, we would still be talking about coherent shapes on C, except for example, all of my brains would get you would get a bi-graded category. Category that's graded by the usual Maslow grading in the mirror, I suppose, and an equivariant grade. Similarly to if I would talk about coherent sheaves, I would get a second grading. This is how the story comes in my world.
I think there's no other thing. I think that, like you have
no.
There is another thing.
There's another thing, which is I can divide by it. So the question is the following, right? In the first way of, in the way I think about an equivariant category, you keep all the harms. The theory has no fewer harms than the original one. But if you take a quotient, you dramatically reduce the number of harms, for example, as well as the number of objects. You lose a lot of stuff. It's not at all the same as the original.
I don't know what that first thing. I'm not sure what you would. What does it mean on the B side?
So it means just working equivariantly. It's the most natural thing you could do. The theory is absolutely beautiful. It is much more beautiful than working non-equivariantly in some ways, and it's very natural for mirror symmetry.
Vivek,
I think
that quotient versus GIT quotient.
No, I don't think she's asking about that.
No. I am not taking any quotients at all.
No. What Mina is saying, now I understand what you're saying. you're saying that since you have a C star action on co-C, since you have a C star action on C, that means that if you take an object of co-C which happens to be equivariant, then there's a C star action on, for example, its self-Hom space, and therefore you get a gradient. That's true.
Exactly. The corresponding category is just a category of gradient modules.
Yeah,
in one variable.
I never discussed that category.
I think you should. I think it's a real. This is how, for example, Hoare and Vafa think about mirror symmetry. They do the first step and then they do the second step of dividing by this action. I think it's very, very natural.
Okay, maybe
not just Hoare and Vafa. This is how physicists think about gauge group actions and equivariance.
Then we should definitely discuss that later. But I want to explain somehow why you would do this. So okay, so the reason for doing all of this is that I want to explain now somehow how you get mirror symmetry for toric varieties. Mirror symmetry for toric varieties is something people know. They've proved it many times, many different ways. But I want to explain somehow a short way to arrive at it. And the idea is for the following. I've already explained to you what is somehow about A1. So I explained to you that Co-A1 is the same as the Fukaya category of this kind of cylinder with a stop. And the idea is that a toric variety, so toric variety, well, it's you can make them as A1, A to the n, minus some kind of bad locus and mod some group. And the virtue of this way of making it is that if I wanted to compute the category of coherent sheaves on this, co of this thing, well, that should be the category of coherent sheaves on AN, which I know. And moreover, I know what its mirror is. And then we discussed already that sometimes in algebraic geometry, deleting a closed subset, that's the same as taking the quotient by the image of its category of coherent sheaves. And now I should take G invariance. Okay, so that the virtue of this presentation of a toric variety is that well, we understand its category of coherent sheaves quite well. And I would like to build the mirror to a toric variety by doing these steps one at a time. And so to explain that, so I'm just going to explain that in maybe a couple simple examples. I have to explain to you what is the mirror to deleting this locus Z, and I have to explain to you what is the mirror to taking this, taking these G variants. And then there's one last thing I'll have to explain to you what the mirror of it is, and we'll get to that in a couple seconds. So first of all, to explain about this, how to delete this Z, I have to tell you how to, I mean, in order to draw pictures, I'm going to have to introduce some convention for drawing scalars in higher dimensions. So let's discuss the mirror to A2, mirror to A2. Well, this should be the mirror to A1 squared. And so it should be some subset. I mean, it should have to do with the cotangent bundle of the two tors. And it's kind of hard to draw the cotangent bundle of the two tors because it's four-dimensional. So the way you draw it is you draw the torus. I've lost my colors here. you draw the torus. And well, I'm trying to indicate some conic Lagrangian inside this torus. So I'll explain in a second why I'm drawing some conic Lagrangian into torus, but first let me just draw it. And the way you draw a conic Lagrangian is you just, first of all, draw what it projects to. And then you indicate which co-directions somehow lift to it. So here I'm going to indicate some co-directions. And so I claim that this conic Lagrangian is the product of this conic Lagrangian and itself. So here, this is a conic Lagrangian. Each one of these is in the cotangent bundle of the circle. And how does this work? Well, each one of these, the product of this like circle union this line, there's a circle and the line, and the circle times the circle gives you the zero section. The circle on one side times the line on the other side gives you maybe this conormal to this line. And the product of the two lines gives you this kind of disk that is here. It's kind of hard to see this picture. So if you've never seen this picture before, maybe one thing to think about is what's happening at infinity. So at infinity, in the cotangent direction, you have the conormal to this circle here, which is a circle. You have the conormal, this other circle here. I'm taking only the negative conormal, so that's another circle. And then you have this kind of region connecting them, which is an interval like this. Okay, so that's one picture to have in your head when you're thinking about this, this mirror to A2. So okay, this is the mirror to A2, and we got it just by, I promised to explain why I was discussing this conic Lagrangian. The conic Lagrangian, it's just a way of keeping track of this stop at infinity. And the stop is just the part at infinity of this conic Lagrangian.
I'm sorry, can you explain the geometry of a conic Lagrangian just one more time? Because just in C, it's just on A1.
In A1, it's the union of the zero section and half a cotangent fiber.
And this is
this
like
union?
How does this make sense as a Lagrangian?
Positive. I mean, it's singular.
Yes. No, sorry, I still don't understand. Why does a half-line Lagrangian make sense?
I'm not going to use it as an object. That's not the role that it plays. Okay, so at infinity we have this thing. It's called the stop. I mean, it's the stop. If you remember, I explained that somehow in A1, if you remove this, that's the same as removing the origin in the mirror. Okay, that was completely illegible. If you have back to A1, removing this removes the origin in the mirror. Okay, and so the way this product worked out, if you remove this, so removing this removes, let's say, the x-axis in the mirror, and removing this, the other one, removing this, okay, maybe I'll just abbreviate. This one has to do with the y-axis, and this has to do with the origin. And you might complain that, well, if I remove the x-axis and remove the y-axis, haven't I also removed the origin? And that's true. And the way, what this has to do with the geometry and infinity of this picture is that if I were to remove this circle, and I also were to remove this circle, then I'm left with this interval, which it somehow contract. I mean, I can now contract it to a point from as far as symplectic geometry cares, and that cannot obstruct the somehow the Rabe flow. So it's not totally obvious from just the picture why in the mirror removing the x and the y axes also removes the origin, but it is true. Okay, so anyway, that's this business of infinity and about removing them and so on. And the reason I drew all of those is I wanted to explain that if I just want to remove the mirror to removing just the origin is to remove just that somehow interpolating region below here. Okay, so this picture now is it follows from the discussion that we just had that this is mirror to A2 minus 0. So that was the first step. I wanted to delete that thing. And so P1 is A2 minus 0 mod GM. And so I want to now take the quotient by GM. And as we discussed, although I'm a bit confused about it at the moment, taking the quotient by GM means unwinding some direction of this torus. And in this case, it means unwinding this direction. So you want to unwind this direction. And what that looks like is, okay, just so you can see it again.
And Vivek, how the action you're quotienting by, how does it? How do we want it to act here? Did you tell us this at some point?
Oh yeah, so I mean, remember in this mirror symmetry, we knew how GM acts on A1, and GM acts on A1. The mirror to the GM action on A1 is you tensor by the line bundle, the local system of that monodrome. And so here, the mirror to this GM action by the same factor on both parts of the A2 is you should tensor by a local system with the same monodromy around both cycles. And if I had gotten straight this piece of category theory, then taking invariance with respect to that action is the same as unwinding the direction along which the direction along, I mean, I want to trivialize that local system. And that means I unwind the torus in this direction.
Sorry, I'm silly. I didn't understand. So you're just trying to get a, we're trying to get a mirror to P1, thinking of it as a quotient of A2.
That's right.
And are you connecting it to the original picture that you gave us of gluing two copies of C?
No, I'm giving an entirely different derivation of it. You will see that it's the same answer, but somehow I want to give the second derivation because the second derivation is going to be correct for all toric varieties. What is that A-side Hartogs?
Actually, I have one more question. Since you are deleting loci left and right, does your A model make sense no matter what kind of locus you delete? Like I can just like decide to delete like some. What are the rules?
Yes, you can delete. You can. So I have something that's I mean, you're allowed to tell me any closed subset at infinity. And then there is some Fukaya category stopped at that closed subset. Now, if you take some like ridiculous closed subset, I will have no chance of computing that Fukaya category. And
Sorry,
so, like, roughly speaking, yeah.
Sorry, any closed subset in infinity. I mean, infinity is already like not part of your set, so we're not really then deleting anything. I'm not understanding.
No, I mean, for this kind of Lyrical manifold, okay, I'll say it precisely. For Lyrical manifold, the point is that at infinity, it's modeled on a contact manifold times a line. And you are allowed to specify a closed subset of that contact manifold.
Vivek, maybe it would be helpful to suggest that before the subset you were specifying had to do with a general fiber of the superpotential, but now you're sort of describing a subset that is not the general fiber of any superpotential. You've somehow like gotten rid of some. You've started with a superpotential and then sort of kind of modified it somehow.
What Ben said is certainly true, but I think maybe it may or may not be related to what Mina was asking. So Mina, let me just answer your question. So let's take the example of T star M. Okay, so let's take T star. And at infinity, mean is the cosine, which I view as living at infinity in T star M. And for any closed subset, S in S star M, there is something well-defined called the Fukaya category of T star M stopped at S. So this is defined. Now, you could ask me, when can I ever compute this thing? And roughly speaking, I have some chance, I have a chance of computing this when S retracts in kind of a symplectic way to a isotropic subset, usually the Lagrangian, usually Legendre. And the typical example of this S is the fiber. I mean, the example that maybe you're used to is the fiber of the superpotential, but it could be anything. And so in this example, when I have the mirror to A2, I mean, as you know, if you write the superpotential for the mirror to A2, its fiber is a 3-punctured sphere. And if you look at this picture I drew over here, which I then erased, that's kind of like the skeleton of the 3-punctured sphere, something which it retracts to. And then I deleted something from that skeleton of the 3-punctured sphere to get over here. But the answer to your question is, indeed, I can do just anything I want. But it's a different question about whether or not I can ever compute that thing.
Thank you.
Okay, so let me get back to this picture. I want to unwind this direction. And so let me just draw what the unwound one looks like. So if I unwind the torus, I get some kind of cylinder. And well, I have one of these ones that's kind of like this. And the other one will look like this. Okay. So that's what it looks like. And I claim, so I mean, I claim, and indeed I have now proven, if you believe this category theory lemma, that I don't know even how to state, that the Fukaya category of this thing, or in other words, of the cotangent bundle of the cylinder with this stop, is coherent sheaves on A2 minus 0 mod GM. What you will notice is that this maybe it's better to say this is the cotangent bundle of S1 squared, comma, this stop. What you will notice is that this thing that I've drawn, it looks nothing like what I told you was the mirror to P2 before, to P1 before. This is co-P1. In particular, it's the wrong dimension. I mean, remember that before, the thing that was supposed to be mirror to co-P1 was the Fukaya category of T star S1 with this stop. And so I have to somehow explain what these things have to do with each other. And so let me explain that. And the explanation is this, I take a slice. Or maybe to say it in more symplectic language, I consider the projection to this real line, and I take the symplectic reduction over this point. And so there's two things to observe. The first one is the symplectic reduction is exactly T star S1 in this thing that I did before. That's just a calculation that you make. You could kind of see it if you're used to these things. And two is that in this case, this category associated with the symplectic reduction is locally constant along R. And it's not so hard to see once you know that in fact the category of the slice is the same as the category of the whole thing. Let me explain about two in this case. The point is that like what happens when you go along this R is that you have your stop looks like this, and the two pieces of the stop, they're kind of just winding around. So you kind of see that, like as you start moving this, if you took a slice here, well, now you would maybe have a picture that.
Can you explain a little in some more detail, what does this symplectic reduction do to your A model? How do you think about that?
In general, I don't know. It is a non-trivial fact that in this case, so maybe it's like in general, there's always a morphism. Yeah, I could have said that. In general, there's a morphism in this direction. And what is not obvious is that this morphism is an isomorphism. To explain why there's a morphism is a bit of a long story. I'd have to explain the full translation into microsheaf theory.
Actually, if I may say something, so in the Horibaffa story, right, what they would have done is that they would have written some superpotential and some big theory, and then reduce the number of directions, you basically just extremize the superpotential. So you put it on the critical locus, and that's that. And on that critical locus, you get your theory on the mirror of P1. And I think that actually does make sense in the A model, in that if you're thinking about it in terms of symbols, right? So if you were just talking about symbols in one dimension, dividing, doing this process of like putting it on the critical locus is a prescription. You keep just one hum, the hum from the most, like if we did it in, say, like just the mirror to C, you just keep one hum, the hum from the symbol to itself with degree 1, the one that's always there. No matter what you do, you deform it, it's always there. That would, and I think that that's exactly what they're doing. So that makes sense physically, and I think it should make sense in the A model more generally, because in the symbol role, just like sitting on the critical locus of a superpotential makes perfect sense. It's now you're just not doing it in all directions; you'll just do it in some direction.
It could be, but let me explain. I mean, let me tell you something that you will have to explain to me before I believe that. So there's one key aspect of this construction, which is that this local constancy. Let me tell you what would have broken that local constancy. If I had not deleted this locus here, if I had not deleted this locus here, then I would still have this kind of thing sitting here. And obviously, I picked that up at some values of this slice and not other values. And that's something which, so in this case, I did delete it, and there was kind of a principled reason for deleting it. But for toric varieties, let me make now a claim. So claim. This works for toric varieties. And actually, maybe that's not the correct way to say this claim. The correct way is that it works for smooth toric stacks. Smooth, Deligne-Mumford, toric stacks. And let me just make a comment about that, which is that in this procedure, as I said, the key point is this kind of local constancy in this direction, because that's what allows, I mean, everything in this procedure up to the last step, when I take the slice, makes perfect sense, Deligne-Mumford or not, smooth or not. But this very last step where I take the slice, that only makes sense, I mean, then you need to check this local constancy. And in particular, it had better be the case that there's no one who you meet at some values and not at other values. And it turns out that exactly the condition that you meet something at some values and not other values, or that rather that you don't do that, is the condition that the fan of this toric variety, because exactly in this case, the fan of this toric space is simplicial, and somehow some thought shows you that's exactly the same as, therefore projects by a smooth submersion to the extra directions. So this fact, it also tells you why in the singular, somehow like in the case of singular toric varieties, or in other words, when that quotient is actually an Artin stack, you will find at other somehow values some special phenomena which appear. And it should be interesting to understand exactly how to think about those in terms of mirror symmetry. And so I would certainly like to understand exactly how this construction I'm describing is related to this Horivafa picture, but some aspect of that is I would like to know how the Horivafa picture knows the difference between a Deligne-Mumford toric stack and a singular somehow toric variety, or something which is actually an Artin stack, or so on. Because what I just explained does know that difference.
How singular are these
somehow,
spaces? Like, I'm not sure actually what these words mean. I know what a toric variety is. How would I make it be into any of these stacks that you're talking about?
Well, this quotient, this quotient an minus 0 mod gm, in general, you would have some kind of an minus some locus mod some torus. This thing, it begins life as a stack. I took a quotient, it's a stack. And when the toric data, when the fan is simplicial, this turns out to be a Deligne-Mumford stack. But in general, it is not a Deligne-Mumford stack. It's some kind of non-Deligne-Mumford stack. And you can form its coarse moduli space, which is the toric variety. This is now, in general, it'll be a singular toric variety. And so the point is that this description that I originally gave in terms of this higher dimensional space gives a correct description for coherent sheaves on this toric stack. And there's a different description, namely taking the slice, which gives a correct description of coherent sheaves on the singular toric variety. And you can kind of see the, I haven't thought about it carefully, but I think maybe Peng Zhou has. You can see the formation of the coarse moduli space as a categorical process in terms of all this, removing this kind of extra stuff that appears only at some specific moments. And I should say that in this singular case, there is no superpotential description. So this is another thing which I would like to understand better about when when the Horivafa prescription works and why it works, when it works, and so on. But I don't understand it. But I do understand this, and somehow that it produces the correct answer.
So, can I ask a question? Maybe there's something I didn't understand about your thing before, but in the singular case, there's some like special values. You see some things at some values and not at other values. Am I allowed to ask, like, what's the category at the general value? What's the category at the special value?
You're allowed to ask, but I have no answer for that question. Oh, no, I do know. I mean, the category at the most special value is, we know by Kuwagaki's work, this coherent sheaves on the singular toric variety. But I don't know, I don't have a proof of that statement along these lines. A posteriori, I know it to be true.
But on a general value?
I have no idea.
So,
I mean, I'm telling you, I don't know. Yeah.
You just finished. I'm sorry. I apologize. I spoke.
No, go ahead.
Yeah. So, in the physics setting, the way toric varieties come in is basically as symplectic quotients. And that in that symplectic quotient, you have to choose the value of some moment map, and that tells you what you are deleting or not deleting, and so forth. And so that's how they live, right? And can we, right? And so so the Horivafa mirror is in some sense knows about the complexification of this moment map. So in particular, it doesn't really know about any phenomena that happen at, you know, on some real co-dimension anything. But other than that, I don't see what's.
I should say this is not the moment map. This map to R. This whole picture, it's happening in terms of moment map or whatever. It's happening at a fixed value of the moment map. What happens when you move around the moment map is you change this locus Z that I'm deleting.
Yeah, right. That's right.
But this whole discussion that I'm having is for Z fixed. It happens at a fixed value of the moment map.
Oh, okay. So okay.
And there's still some kind of spreading out of this, like the stack, its category, for some reason I don't really understand, is most naturally viewed as somehow global sections of some family of categories over some vector space. And when the stack is Lee Mumford, it's a locally constant family, but in general, it has a much more complicated behavior.
Okay, so I'm not understanding because, oh, let's see. Oh, there's some chat, so maybe we should read it all before I.
This chat is Justin trying to answer my question, and maybe succeeding in answering my question about how I should formulate that category theory lemma from before. Justin,
Okay.
can you do me a favor and once you finish with this answer, email it to me also?
Yeah, I mean, I'm
not sure how.
I'll also email it to you.
That'll be great because I'm not sure how to keep this thing.
So this equivariant Fukui category you mentioned, can I think of this as the Fukui category of some kind of quotient stack, if such a thing was well defined, or is it something different?
No, it's a different equivariance. I'm not acting on it. It's not a geometric action on the the symplectic manifold target space. It's an action on the category which comes from tensoring by local systems on that space. It's like it's mirrored to a geometric somehow C-star action, but it is not itself that kind of action. And the thing which I believe to be true and is maybe explained by these comments of Justin in here is that there's a formal way to explain that, like, if you're tensoring by local systems, that's the same as, trivializing tensoring by local systems should be the same as trivializing the topology which gave rise to that local system in the first place, which is means you take cover.
I see, yeah, thanks. So somehow on the algebraic geometry side, it is just like a geometric action. Like you have an actual action on the space, but on this side, you don't have an action on the space, but only on the category. But yeah, I wonder if, so you can formulate, so you can write the category of coherent sheaves on a quotient as a limit or some limit of some cosimplicial object where it will start by the first two maps will be like coherent sheaves on X map to coherent sheaves on X times G via either projection or action map, pulling back along those maps. Yeah, so anyway, like a geometric action on the space gives you some kind of cosimplicial object at the categorical level, and on this Fukui side, you don't have the you don't have the action on the space, but you have.
Let me answer.
It sounds like you still have the cosimplicial object that you could just take the limit of. Sorry.
Yeah. I mean, maybe that's one way of proving the statement. If you were to do that, you would discover that you've written down the description of like BS1. I mean, you have like Fukui category, and you like make this cosimplicial object, and there'll be many copies of somehow, this thing, and that explains like why it is that you're supposed to take this like cover. I mean, I think the discussion you're having is if one were to write a proof about why is it true that trivializing the action by local systems, by some kind of like abelian local systems, is the same as taking a cover. I think maybe you're explaining how you would prove that statement.
Yeah, I see.
In terms of you like build a simplicial, you build this kind of simplicial model for BS1.
Right. Yeah. I guess this is just sort of answering maybe the question of like how to precisely define this category when you have something which is not just like a finite group but some kind of V group or something.
Oh, I see. You're explaining to me what this means. And you're saying that I should view this as some kind of limit of C and then C cross some G, like some kind of co-G or something.
Yeah, exactly. So sort of by analogy with algebraic geometry, like if you did this thing to coherent sheaves, the category of coherent sheaves on some X, that would be equivalent to the category of coherent sheaves on the quotient stack. So from that sense, it looks like a plausible definition.
I see. So you're saying that rather than the data that, I mean, rather than me just somehow casually say I tensor by the local system, I have to actually produce an action of the category of coherent sheaves on C star.
Yeah, I guess to be
so
technically, if everything is secretly like an infinity category, then technically you would need this to produce some kind of co-simplicial object like that. I think, yes.
Okay. Yeah. Thanks a lot. That's helpful.
Sure.
Maybe I have a question, maybe in the same direction, so maybe I should ask it now. Vivek, is there any case about these equivariant Fukaya categories where you can interpret them as not having come from a geometric action of the space, but you're taking a Fukaya category with coefficients and something else? Hello?
I mean, I think in some sense, yes. You're taking like Fukaya category with coefficients and graded. I mean, like what does it mean to take a cover? It means you take Fukaya category with coefficients and like graded vector spaces, right? Because like you have on the cover. I mean, like if you're taking just in terms of local systems, if you want to take like local systems on the cover, yeah, maybe I'll redirect your question back to yourself. If you have a space and you want to describe local systems on some cover of that space, then how would you describe that as local systems on your original space with coefficients somewhere? I think that's the question you're asking.
Yeah, I see. That is the question I'm asking. But I guess what I was asking sort of more concretely, like in the example you just showed.
I don't have a more concrete answer for you.
Okay. Anyways, thank you.
But yeah, I think before this discussion, maybe we already said it. I want to emphasize this slightly strange picture where this kind of this category it comes over this vector space. There's some like various interesting phenomena happening in codimension, loci various codimension. Because I'm not really sure how to think about that picture. Okay, so that was some long discussion about toric varieties, which anyway everyone already knows mirror symmetry for toric varieties. So why was I discussing it? Well, I wanted to explain somehow maybe the answer. So this was supposed to be some. Let me just say the answer. So the theorem, which by a different proof was originally by this Fang, Liu, Truman, and Zaslow, and somehow the completion of it by Koyaki. And I think other people have proven it as well. Is that the coherent sheaves on a toric variety. So this is the fan of the toric variety, is the same as the Fukaya category of T star S1 to some power with some particular stop, where if lambda sigma equals, it's the union over cones and sigma of this kind of orthogonal to the cone times the cone. Okay, so some formula. Let me say one word about the proof of this theorem along the lines that I said so far, which is I want to explain how it is you get this local constancy. So the local constancy comes from the fact that the skeleton, this kind of the stop for the ambient space, this somehow this ambient space is itself the skeleton of some Weinstein manifold. And the cartoon of that is, remember that in this very simplest example of the mirror to A2, the thing at infinity, it looked like this, and you're supposed to view that as coming from the following manifold. You first, like you have the kind of cotangent bundle of two circles, and then you attach a handle like this. Okay. And the thing which is true for in this case of simplicial toric varieties and not true in general is that such that the handle attachment data projects somehow smoothly to maybe let's say is a bundle over this auxiliary vector space. In the general case, some of these handle attachments happen only over like special values and so on. And so that's somehow the key point. And so because this handle attachment data projects, it makes a bundle, then this kind of symplectic reduction is compatible with forming this skeleton of the Weinstein manifold, and you can convince yourself everything is constant. But I wanted to explain that's the key point. Yeah.
Okay. Firstly, I'm gonna have to go into the car, so I might lose you. But
okay.
I think hopefully not. So the thing is, I have to pick up my son because this week he actually is back in school. But so this local constancy, I think I know what you're asking about. For example, let's talk about the P1 example. I could have written down the wrong superpotential, which would have been something like instead of like y plus y inverse, it could have been anything whose product is 1, but it could have been like y to the n plus y inverse to the minus n. Is that kind of the thing we're asking about? Why not that? In other words, there's some place where they have to solve an equation. And there's a question, which solution do you pick? Is
I don't
that
know.
the
I
kind of thing
haven't.
that sounds like this local constancy you're asking about.
Well, it's possible. I mean, you have to tell me more.
Okay. Okay.
Yeah,
That's the one place where they have to make a choice. That's the place where they have to make a choice.
To give you an example where this local constancy fails, I would have to go to at least 3 dimensions. I would need a 3-dimensional toric variety to produce the first example that fails.
Okay.
So it's kind of, yeah,
Okay.
it's not so easy to give the example.
Okay. Okay. Okay.
But
Right.
it may be related to other things that somehow have similar behavior. So maybe the reason I began the talk in this way, although, you know, like at what point, is that I wanted to, this business of understanding this boundary as a handle attachment is the key to proceeding further and gluing together these toric varieties. So let me say a few words about that at the end. So now finally we arrive to the title of this talk, which is Gluing the Mirror. And so what is this about? It's we've been studying toric varieties so much because in general, one is interested in the large complex structure limit. Where this space, the coherent side Y is a union of toric varieties, which is glued somehow out of toric varieties, glued along toric varieties. So just some examples. If it's supposed to be the limit of some kind of deformation. So like for instance, if I was taking the limit of an elliptic curve, maybe its limit is like 3 P1s. Or if I have a K3 surface, it kind of degenerates. I'm never going to draw this like 3 P1s anymore. I'm going to draw it like a triangle. And actually it's important which triangle I draw it as. I draw it like this triangle. And the K3 surface, I mean, it goes to 4 P2s, and it's some kind of tetrahedron. And that's the large complex structure limit. And since we understand, the idea of this gluing the mirror is that so now this is, finally we say something new, and this is work with Ben Gamage. And so since we understand toric varieties, that somehow mirrors to toric varieties, and we understand the mirror to gluing algebraic varieties, gluing along toric varieties. Well, we can just glue the mirror. We glue the mirror. So let me explain what this looks like. So maybe the first example of this is for this like 3 elliptic curves, and I explained that well, the mirror geometry to the P1 somehow you're supposed to think of it being captured by this kind of skeleton, which is a circle and this kind of segment. And I take 3 of them. And the prescription of gluing the mirror tells you, well, you just glue it up. And so now this should be the skeleton for the mirror to 3 P1s glued together. And this is true. So more generally, in the existing paper of Ben and I, we showed this works for hypersurfaces in C star to the end. And we're now in the process of writing something which says it just works in complete generality. So what do I mean? So in general, here's the general case. The general case. You take a manifold B, this is a manifold, and it carries a cell with a cell decomposition. And you ask that the normal bundle, the normal bundle to each cell is identified with the fan of a toric variety, in such a way that like you have the appropriate compatibility of going from one cell to the cells in its closure and so on. And from this data, you can produce two things. One is, well, the normal bundle to each cell is the fan of a toric variety, so you produce a toric variety. And the cells are glued together, so you glue together the toric varieties. You produce a somehow union of toric varieties. And on the other hand, you produce also a symplectic manifold. And let me just say a few words about how you produce this symplectic manifold. I mean, this talk has been already a bit long, and so I'm just saying a few words about how you produce this symplectic manifold. But the punchline is because of the way, like, essentially by construction, you have some kind of automatic mirror symmetry. Because we know all the pieces, we know about gluing. And so let me just say a few words about how you produce this symplectic manifold. And maybe I'll just draw like one cartoon of it. So, well, I already drew one cartoon, which was kind of this one. So I'll just draw the next dimension up cartoon. So if this the space B it's always confusing about whether you use B or the dual space of B. I want to use maybe the space B. Maybe the space B maybe looks something like this. I'll just draw some local piece of it. And what you're supposed to do is you're supposed to put a, in this dimension, like two torus at each vertex. And since I see something at this vertex, okay, I didn't want to do that. I see something at this vertex here, namely I see the fan of P2, and so I make the mirror skeleton to P2. And well, I've now given you some kind of outline of proof of how to compute that, I mean, how to discover that for yourself if you wanted, and a proof of mirror symmetry for it, and this mirror skeleton, it looks like this. Okay, this whole conormal here. And as you see, this mirror skeleton, it has three somehow one-dimensional strata with their conormals. And what you do is you like make coming out along these three edges, you put that comes that conormal. And there's also this zero stratum, and that zero stratum in its conormal is identified with the base manifold itself. And then you do the same thing for these other P1s, and so you make this kind of conormals attach here. This is really a family of circles. It's like a tube. This is like this drawing is getting worse and worse. Let me start it over. Okay, so this kind of, let's try again. So we have these cylinders, this tori, and then going along this edge will be some kind of cylinder, which is, and then this edge is kind of cylinder, this edge is some kind of cylinder, this edge is cylinder, this edge is cylinder, this edge is cylinder. I mean, maybe just to say, this is a T2, this edge is like an S1 times an interval, and then this conormal to the point, that's a disk, and that's the disk which we're building this base manifold out of. So we somehow this region is that disk. And I've explained to you now how to glue these somehow Lagrangians together, and you get some kind of cell complex, whatever. And the statement, which maybe is not so hard to see, is that this is the skeleton of a symplectic manifold. And the way you see that is, well, I begin with these tori. And I take their cotangent bundles. And then these one cells coming in, then I, the next one's up with these ones. And if you think what that is, well, what it is, it's a circle's worth of one handle attachment to this thing. And so you attach the one handle. And then the next step is you have to do something about these ones. And that's just a two-handle attachment. Specifically, I attach this two-handle and this kind of like, you haven't seen the ends of these two handles, but these ones also. And so on. And then you build up the manifold in this way. And the resulting manifold, essentially by construction, it's just glued together of these pieces, which I already understand, and thus you get this equality. So maybe let me just state one kind of theorem. So theorem, which is this Bengamage, is that there exists a construction which I've kind of outlined for you of a symplectic manifold mirror to any somehow such union to somehow appropriate unions of toric varieties. Such that homological mirror symmetry holds. And maybe I want to emphasize that this is an easy theorem. It involves some kind of setup and gluing together, but by now all of the pieces are kind of in place to just assemble all of these things together. There's kind of somehow a program after this having to do with, we want now to deform away from large volume. And that's a long story for another day. I think maybe this has been enough for one day. Okay, that's it. Any surviving listeners
Hi, Vivek. I
Yeah,
wanted to
Alexander.
ask you what type of symplectic manifolds do you get? Or I guess my question is, given a symplectic manifold, can I tell if it's if it could arise from something like this?
Yeah, that's a good question. I mean, there's supposed to be an answer, which is that like Gross and Siebert have some prescription where from something roughly speaking of this kind, this kind of data of a manifold with triangulation, this kind of data. Yeah, maybe I'll comment about that. So what did I say? A manifold with a cell decomposition and normal to each bundle, the normal bundle to each cell is identified with a fan. And what that means, it's kind of like in the normal directions to each stratum, I have kind of an integral, I have this kind of affine structure.
Mm-hmm.
But I don't have that structure like along each stratum. And so I could, for instance, begin in the setting of this Gross-Siebert business, and then I would have that, the Gross-Siebert setup always gives me such an object. And if I take, in that setup, they supposedly tell you about at least the, like symplectic manifold, which is supposed to be the mirror. And it is at this point, strictly speaking, conjecture, although we have some ideas how to prove it, that we get the complement of a divisor in their purported space. So that, I mean, that's supposed to be the answer. And the methods to prove that are like more or less whatever kind of tropical geometry methods we used in the previous paper.
I see, thank you. Okay, since no one's asking, so maybe we should ask a clarification. How should I know that I see any sort of integral affine structure on the normal to each stratum?
Oh, I mean, like I said that the normal to each cell, I fix a diffeomorphism to the fan of a toric variety, and that's like
I see.
That's a very rigid structure.
I see. So that is I see. Is that some extra data that goes into this isomorphism between this mirror symmetry that you described?
I mean, I need this data in order to produce this side.
Uh-huh.
I mean, for sure, right? Because it's like toric varieties. But I also need it to produce this side. And the way I use it to produce this side is that this business of making above each stratum the FLTZ skeleton, like saying how the FLTZ skeleton sits above the stratum, I need some, maybe the best way to say it is the following. In the FLTZ skeleton, inside the cotangent bundle of the cotangent fiber over the most singular, the central, the zero in the torus, you see the fan of the toric variety, like just the union of those cones. And so if I have any prescription for gluing together FLTZ skeleton, I can ask, what does it restrict to on that fiber? And on that fiber, it had better be something about fans of toric varieties. And conversely, you can basically reconstruct the gluing of the whole skeleton from how you glued the fans of the toric varieties. That's how it interacts with the other side.
I see. Yeah, I was just confused because I didn't see how it went onto both sides, but now that you mentioned it, it makes sense.
I mean, the one way to think about it is that, I begin with this manifold B, and you should think about B, just imagine it comes as the cell decomposition comes as like a Morse cell decomposition, like you attach these handles of B itself. And this business of these normal bundles to each cell is being identified as fans. That's the data I use to lift the cell, this Morse decomposition of B to some kind of Morse decomposition of a symplectic manifold. because like for the vertexes and the vertices in B, I give you a some kind of torus, and then I have to tell you when I'm attaching the cell. Well, first of all, I'm attaching n-1 family of torus family of cells, and I have to tell you where I attach it. There's like a circle's worth of choices about where to attach that one. And then, so I have to specify basically somehow 3 points on, a point on a circle for each one of those. And then for the 2 cell, I have to specify like a point on a 2 torus, where exactly I attach it, and so on. That's the.
Does this B? It sounds like this B sits inside of your symplectic manifold somehow.
B sits inside. I'm always confused about this. I don't think that's true.
No, I mean, B is the, oops, sorry, I need to, oops, sorry. Sorry, B is the, B is supposed to be the base of a fibration to the manifold.
No, I mean, that's
in
true.
Fukaya category theory, the point is, if the SYZ fibration has a section, that usually means you're mirror to an algebraic variety. And the section kind of is mirror to the structure sheaf. So the B also kind of does live in your symplectic manifold.
But is that true that this description I was saying about like you glue together these cotangent fibers, does that provide us this section? I mean, that'd be pretty good if we can have a section.
I claim that it does. Yes.
I mean, it sounds like each of the local pieces you have has a copy of B sitting inside of it somehow.
Yeah.
But whether they match it or not.
I mean, this is the thing about, if you have a sphere in B, I mean, it's this Legendrian sphere, it lifts,
Well, we should definitely think about that. That's a very good point. Does that B sit inside?
Yeah, I mean, although maybe not in, I mean, so, there's this famous example in the beginning of Abu Zaid's ICM address of a SYZ fibration that doesn't have a section. And so the thing is only mirror to coherent sheaves twisted by a gerb on some variety. So it could be that you can create a B that does not have a section. I don't know. I mean, create a B and a SYZ fibration to it that doesn't have a section.
No, I mean, that could be true, but it seems like the prescription that we just that I just described right now, it's gluing those fibers together. So it seems like it's building a section along with the. We should think carefully about it, but
yeah.
okay. I think maybe people are out of questions. Is that?
Vivek, I'm sorry, I had lost you guys for a minute, and now I'm back. So,
Oh, hello.
Yeah, I was okay. So I'm afraid I lost some section, but I think I can review it. I don't want to make you repeat all of it, so it wouldn't be fair. So, thank you.
We can talk some other time.
Okay, yeah. So right. So I'm afraid okay, good. Yes, I will review what happened. So thank you so much for anytime Vivek tells us everything he knows about mirror symmetry, obviously it's going to take a long time, and I'm sure you still didn't tell us everything,
Well, thanks for the invitation. I hope you guys enjoyed it.
This is great fun. Okay.
Yeah.
All right. Okay. Take care.
Bye.
Bye-bye.
Bye-bye.
Thanks, Vivek. Bye.